My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about a lot of expressions, a lot of definitions used in electricity. Definitions such as electric current intensity, ampere, coulomb, potential difference, volt, electric energy, power. Also, we'll learn about electric resistance and the factors affecting the resistance. Hopefully, you'll benefit from it. So let's get started. Electric current and Ohm's law. First of all, let's define electric current. What's meant by an electric current? Electric current is flow of electrons in solid conductors. Okay, let me say it again. It is flow of electrons. In general, it is flow of electric charges in solid conductors. And now, what's meant by electric current intensity? Electric current intensity is denoted by capital I, and it is calculated from the expression I equals Q over T. So electric current intensity will be, yes, the quantity when the time is equal to 1 second. Okay, now let's define it. Current intensity is the quantity of electricity that passes through a conductor in 1 second. Current intensity, it is the quantity of electricity that passes through a conductor in 1 second. Current intensity is measured in amperes. So talking about the SI unit of current intensity, it is ampere. Okay, since I equals Q over T, so ampere equals coulomb over second. We want to define ampere. Okay, it is unit of current intensity. So we should start with current intensity. It is the intensity of the electric current. When the rate of flow of electricity is coulomb per second, when the rate of electricity is 1 coulomb per second. This was about the definition of ampere. And what about the definition of coulomb? Since coulomb equals ampere times second, okay, so what about coulomb? It is the quantity of electricity which passes any point. It is the quantity of electricity which passes any point in a circuit in 1 second when a steady current of 1 ampere is flowing. And now, what about the amount of a charge carried by just 1 electron? A charge of 1 electron, and it is denoted by a small e, it is equal to 1.6 times 10 to the power of negative 19 coulomb. So talking about the charge of 1 electron, it is equal to 1.6 times 10 to the power of negative 19. Okay, now we'll do something very useful. We want to know the number of electrons altogether that carry a charge of 1 coulomb. Okay, so we've got a column here, we've got a table. In the first column, we've got the number of electrons, and in the other, we've got the charge. And I've just mentioned that the charge of 1 electron is equal to 1.6 times 10 to the power of negative 19 coulomb. And we want to know the number of electrons that carry a charge of 1 coulomb. It's all easy. It is 1 over 1.6 times 10 power negative 19. So if we want to calculate the number of electrons that carry a charge of 1 coulomb, it is 1 over 1.6 times 10 to the power of negative 19. Actually, it is 6.25 times 10 to the power of 18 electrons. So once again, 6.25 times 10 to the power of it. So once again, 6.25 times 10 to the power of 18 electrons carry a charge of 1 coulomb. We've got very useful pieces of information. Milliampere, and it is denoted by small m capital A. Okay, if we want to convert it into ampere, it is multiplied by 10 to the power of negative 3. And what about microampere? It is multiplied by 10 to the power of negative 6 to convert it, to change it into amperes. Okay. Since Q totally charged, Q denotes the totally charged, okay, it is equal to the charge of one electron, small e, and n is the number of electrons. So E is the charge of one electron, n is the number of electrons. So number of electrons can be calculated by, of course, totally charged, which is denoted by Q, over charge of one electron. And don't ever forget, charge of one electron is equal to 1.6 times 10 to the power of negative 19 coulomb. And now talking about direction of electric current. As a matter of fact, we've got two directions. Okay, in front of you we've got a circuit, very simple one. Yes, it contains a battery denoted by VB. Small r denotes the internal resistance of the battery. And we've got a load denoted by capital R, or a resistance, all connected in series. And what about the direction of the current? Talking about the conventional direction. Conventional direction, it is flow of positive charges from the positive terminal to the negative terminal outside the cell. This was about the conventional direction of the electric current. It is from, yes, the positive terminal to the negative one outside the cell. And we've got another direction, as I mentioned. Yes, it is the opposite one. It is from the negative terminal to the positive. It is the direction of flow of electrons, or direction of electron flow. Once again, it is from the negative electrode to the positive. Here, electrons are flowing. When we talk about the conventional, the current is regarded as flow of positive charges. Okay. And now we want to define something very important. It is potential difference between 2 points in a circuit. Potential difference, or voltage, or potential drop, is denoted by capital V. What about it? To define it, we want, yes, a mathematical relation, mathematical expression, so as to be able to define it. So potential difference is equal to W over Q. So it is the work required to transfer unit charge between these 2 points. Okay, so potential difference, it is the work required to transfer unit charge. Unit charge means 1 coulomb between these 2 points. Volt equals, yes, since, as I said, V is equal to W over Q, V potential difference, W is electric energy or energy, Q is charge, amount of electricity. So unit of potential difference is volt, unit of energy, electric energy, is joule, and of course coulomb is the unit of quantity of the charge. So volt is the potential difference between 2 points when a work of 1 joule is required to transfer 1 coulomb between these 2 points. Okay, also there is another definition for volt. Okay, it is the potential difference between 2 points when a work of 1 joule is required to transfer 6.25 times 10 to the power of 18 electrons, because this number, this figure, carries a charge of 1 coulomb. So it is the potential difference between 2 points when a work of 1 joule is required to transfer 6.25 times 10 to the power of 18 electrons between these 2 points. And we've got something very similar to potential difference. It is V battery or electromotive force of a cell. What's meant by electromotive force of a cell? Okay, as I said, it is denoted by EMF or V battery. It is the work required to transfer 1 coulomb, unit charge is called 1 coulomb, through the whole circuit. Whole circuit means external circuit as well as the internal circuit. So it is the work required to transfer unit charge through the whole circuit. That's to say through the external circuit as well as the internal circuit. Also, there's something very important, and we'll explain it in details later. EMF of a cell is the terminal voltage when no current flows. Another important definition, EMF of a cell is the terminal voltage of the cell when no current flows through it. Okay. And what about electric energy? And we want an expression to calculate electric energy. Okay, electric energy is denoted by, W. Okay, since V, potential difference, is calculated from the formula W over Q. W is the energy, Q is the charge. So energy equals V times Q, VQ. This is equation number 1. And since current intensity is calculated from the formula I equals Q over T, so quantity of electricity equals I times T. This is the second equation. From equation 1 and 2, it's all easy for you to, it's all easy to get the expression that gives you the electric energy. It was VQ, and substituting for Q, it will be VIT, VIT. So from 1 and 2, we can say, W electric energy is equal to VIT. V is potential difference, I current intensity, T is the time. Electric energy, since it is equal to VIT, so energy is measured in joules, potential difference in volt, intensity in ampere, and time in seconds. So joule is equivalent to volt times ampere times second. And what about electric power? Electric power is the rate of conversion of electric energy. So it is electric energy converted over time, or it is electric energy converted in 1 second. So electric power equals energy over time. So power is measured in watts. SI unit of power is watt. Watt is equivalent to joule over second. Since power equals VIT over T, power equals, work over time. Energy, we managed to obtain an expression for it. It is VIT, VIT, over time. T will be crossed out. Okay, so power is calculated using another expression, VI. So we can say watt is equivalent to volt times ampere. Okay. And now talking about something very important. It is Ohm's law. What about Ohm's law? It is the law that enables us to define electric resistance. Okay, it teaches us about electric resistance. What about it? Okay, first of all, what is meant by electric resistance? electric resistance is denoted by capital R. The resistance of a material actually is its opposition to the flow of electric current. Let me say it again. Resistance of a material is its opposition to the flow of electric current. It is denoted, as I said, by capital R and measured in ohms. Kilo ohm, to convert it into ohm, it is multiplied, yes, by 10 power 3 and mega 10 power 6 to convert it into ohms. And now, okay, what about the statement of Ohm's law? Actually, it states that the current flowing through a conductor is directly proportional to the potential difference. Current flowing through a conductor is directly proportional to the potential difference across its ends, across the ends of the conductor, provided the temperature is constant, unchanged. Okay. So the ratio between V, potential difference, and current is a constant. We call it resistance. Okay, so V over I equals R. So we can say volt over ampere is equivalent to ohm. This is one thing. Also, we've got another statement for Ohm's law. What about the second statement? Yes, the ratio of the potential difference across the terminals of a conductor to the current intensity flowing through it is a constant called the resistance of the conductor. Okay. And now, how to calculate, how to measure the resistance of an element? Okay, in front of you we've got a circuit that consists of a switch, okay, a battery, a rheostat, a meter, and a resistance. So once again, it consists of a switch. It is the control of the circuit to switch it on or off. And battery, okay, rheostat to change the resistance of the whole circuit, a meter to measure the current intensity, and the resistor. And they are all connected in series. Okay, and now we've got, yes, a device connected in parallel to the resistor. It is the voltmeter to calculate the potential difference across the resistor. So we've got a device that measures the current intensity that flows through the resistor. It is the ammeter. Potential difference across it is measured by the voltmeter. Okay, we have to, yes, switch it on. Circuit is closed, current flows. The reading on the ammeter is noted, and that on the voltmeter is noted also. By using the rheostat, we change the resistance of the whole circuit. Current changes, and it is measured by the ammeter. Also, the potential difference, it changes. We'll repeat this step, and we'll plot a graph between potential difference, okay, versus current intensity, and we'll obtain a straight line that passes through the origin. The slope of the graph, what about the slope? It is tan theta. What about it? It is opposite over adjacent. So it is potential difference V over current intensity I, and it will give the resistance of the conductor. Okay, it is equal to R. And now talking about the factors affecting the electric resistance of a conductor. As a matter of fact, we've got 4 factors that affect the electric resistance. First of all, length of the conductor. Length is denoted by capital L, and we've got a direct relation between resistance and length when the rest of the factors are kept constant, unchanged. So R is directly proportional to L. Second factor affecting the electric resistance is the cross-sectional area, thickness of the wire. Cross-sectional area is denoted by capital A, but we've got an inverse relation. So R is proportional to 1 over A. Okay, this is the second equation. And once again, this is quite correct, but other factors should not be changed. Third factor affecting the electric resistance is temperature, and finally kind of material. From the two equations, first which is R is directly proportional to L, R, yes, proportional to 1 over A, so we can say R is proportional to L over A. Proportionality sign is converted, is replaced by equality sign, okay? So a constant appears. Yes, it is denoted by rho E. And what about rho E? It denotes a specific resistance, and also it is called resistivity. So R is electric resistance, rho E is resistivity, L length of the wire, A is cross-sectional area. Okay, once again, this constant is known as the resistivity of that material, or a specific resistance. We want to define resistivity. Resistivity of a material, as a matter of fact, yes, depends on temperature. It changes, okay, two factors only affect resistivity. Yes, kind of material and temperature, okay? At a given temperature, it changes by changing the kind of material. So defining resistivity of a material at a given temperature. What about it? Okay, let me help you to be able to define it. Since R is equal to rho E L over A, so resistance will be equal to rho E when the length is equal to 1 ampere, area is equal to 1 meter, and area is equal to 1 meter squared. In this particular case, we can say, yes, resistivity of a material is the resistance of a wire of that material, 1 meter in length and 1 meter squared in cross-sectional area at that stated temperature. Unit of resistivity, it is ohm meter, okay? Unit of resistivity, it is the product of ohm times meter. And now we've got the question, what's meant by resistivity of copper at a given temperature is equal to 1.69 times 10 to the power of negative 8 ohm meter. Okay, if I give you this piece of information, resistivity of copper is equal to 1.69 times 10 to the power of negative 8 ohm meter. What do you understand from it? Okay, thank you very much. It means resistance of a copper wire, 1 meter in length and 1 meter squared in cross-sectional area at that temperature is equal to 1.69 times 10 to the power of negative 8 ohm. And now talking about conductivity of a material. It is sigma. It is the reciprocal of resistivity. So it depends on two factors only, kind of material and temperature. It is the reciprocal of resistivity. Sigma equals 1 over rho E. So unit of conductivity is ohm negative 1, meter negative 1. Ohm negative 1 is called Siemens, by the way. Okay, so unit of conductivity once again, ohm negative 1, meter negative 1, or Siemens, meter negative 1. Resistivity of a material, as I said, depends on the kind of material and temperature. And now we've got another question, what's meant by conductivity of silver at a given temperature. Conductivity is equal to 6.173 times 10 to the power of 7 ohm negative 1, meter negative 1. It's all easy. All you have to do is to convert it into resistivity. Resistivity equals 1 over conductivity. So rho E equals 1 over 6.173 times 10 power 7. It is 1.62 times 10 power negative 8 ohm meter. And now we can say, yes, the resistance of a wire of silver 1 meter in length, 1 meter squared in cross-sectional area at that mentioned temperature is equal to 1.62 times 10 power negative 8 ohm. And now talking about practical determination of electric conductivity of a material. First of all, get a wire of that material, yes, and measure its length and its cross-sectional area. Okay, and what about the second procedure? Use Ohm's circuit to determine the resistance. Let me remind you with Ohm's circuit. I've just explained it. It is shown in front of you. The circuit that consists of a switch, battery, rheostat, ammeter, resistor, and a voltmeter connected in parallel to the resistor. Use this circuit to determine the value of the ohmic resistor of the resistor. Okay? Calculate the resistivity using the expression R is equal to rho E L over A. Okay, and if you manage to calculate resistivity, it's all easy for you to calculate conductivity, of course. Conductivity is equal to 1 over rho E. This way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.